Yeah, so today I'm going to talk about growth and remodeling of cardiovascular tissue. But this is not a research presentation, although like if we finished after 1.5 hours and everybody is bored, obviously we can also dive a little bit more into like the latest and greatest research. But my idea for this talk, I actually like for the first time in a long time started making from scratch, is to show you more like some mathematical methods that we use for growth and remodeling, just give you like a little bit of an overview of things that are out there. And with a lot of help from Claude Code, I also created a GitHub repository that has these slides, but also like a little bit of Python code. And so like throughout this like seminar, there will be like little examples where you can like run like the tiniest like growth and remodeling examples and like just see how tissue adapts for yourself. Maybe to get an idea of what people's background is, who here has worked with growth and remodeling models specifically? Okay, okay, 3, yeah, okay. Who does anything with cardiovascular tissue? Okay, okay. Who knows what a deformation gradient is? Okay, okay. What? Maybe this side of the room. What is it? don't want to point anyone out. What's your background? What, computer science or chemical engineering? Okay, okay, okay. Who knows what an integral is? Yes, an integral. Yes. Okay, nice. And who knows what a derivative is? Nice. Okay, okay. Then I think we should be fine. Okay. And as I said, like I made these slides from scratch, but making them from scratch means I copied them a lot from other people. So these are Amadeus Gebauer, who just finished his PhD also in Wolfgang Wald's group in Munich. He worked on cardiac remodeling. Jonas Eichinger did his PhD with Wolfgang Wahl, Christian Zyron, and Jay Humphrey. And then, yeah, Jay Humphrey, you will see later, is the person who developed a lot of these methods I am talking about today. In general, what even is growth and remodeling? So except for the select few that have worked with this before, so growth in general is a change in mass of tissue, and remodeling, very broadly speaking, is some change in microstructure. So that's why we differentiate between growth just means something gets bigger or smaller. Remodeling means somehow its structure changes. And today, yeah, we learn a couple of different mathematical theories how to simulate those. And this, yeah, so I will start with like a brief introduction to mechanobiology in blood vessels. And this goes back quite a while. So the top is Davy's law, so that ligaments or any soft tissue, when put even under a moderate degree of tension, if the tension is unremitting, will elongate by the addition of new material. That is the saying, if you have tissue, you pull on it, it doesn't stay in this pull configuration, it will add new material, and then over time it probably will get longer. And there's also something by Julius Wolff. It's a good example of only half a German sentence. This is all half of a sentence. But in basically what he's saying is that also bone mass is proportional to load. So if you put a higher load on the bone, you will get more bone. And if you stop using it, think of like astronauts on the ISS for 1 year. If they completely stopped using their bones, like their bones probably would shrink to an extent that if they came back after 1 year and they would take a few steps, yeah, they would, I don't know if you can say they would break immediately, but like they daily exercise so they don't lose the bone mass, because this is all related to how they are yeah, mechanically loaded. So that's kind of cool. And I also would say, so now my research group does biomechanics, and I think this is also like, I would say, the coolest fact about doing biomechanics compared to any other engineering. As like my background is mechanical engineering, so I learned about steel and other things. But the unique thing about biological tissue is it adapts. If you load it in a different way, it will adapt to that loading. Steel, you can like simulate how it will break. You can study fatigue and other things, but it will never adapt. And so today we are learning some mathematical theory of how living tissue can adapt to different loads. And why is this important? Or like the talk also had specifically vascular tissue in the title. Why is this important specifically for vascular tissue? So this is like a graph that's shown a lot. that was adapted by my former colleague. So here you can see all these little dots are all different animals, and it goes from a mouse on one end of the spectrum, a little mouse, maybe like 20 grams, to all the way up here, you have a pig that's maybe like 200 kilograms. And in all these different elements, oh yeah, so here they are plotted by weight, so it ends here at 200 kilograms. And for all these different animals, they measured or like estimated the tension in the aorta. So tension has unit newtons per meter, and you can see, so one remarkable thing is already, so between the lightest and the heaviest animal, you have 4 orders of magnitude, but the tension only varies by a factor of 26. So something seems to be keeping this tension, that variation in tension much, much lower than like the overall mass of the animal. And then you can take it one step further. If you compute tension per lamella, so like the aorta has different layers, and if you normalize it by these layers, so what you're eventually doing is you're dividing the tension by the thickness. So in the end, what you're computing is the circumferential stress. If you look at that, it only varies by a factor of 2.8. So if you compare the mouse aorta to the pig aorta and also the human, somewhere in the middle, they all have a remarkably similar tension in the aorta. And the reason for that is there must be like some, or one theory would be there must be like some adaptation mechanism that keeps all these different animals at a more or less constant circumferential stress. Can anybody think of why, maybe we should have started with that, why is it even important to study that? Like, can anybody think of like, why is it important that we study how a mechanical load on a blood vessel changes the blood vessel? Like, why do I get paid to do that? Why is anybody finding that relevant?
Blood pressure?
Yeah, blood pressure. What can happen with blood pressure?
It could go high.
Yeah.
Have diseases with that?
Yeah. So yeah, high blood pressure causes many problems. So that's why I actually don't know how it is in Germany, but in the US, every time I go to a doctor, even like for a cold, like they take my blood pressure to just monitor. Yeah. Can people think of other things that can like mechanically disturb blood vessels? Maybe other diseases?
Aneurysms?
Aneurysms? Yeah. Does everybody know what an aneurysm is? Yeah. Or do you want to explain what an aneurysm is?
Aneurysm is where your blood vessel gets too big, so it grows naturally and at some point may rupture. So there's clearly something wrong with the homeostasis in your wall up to the point where it can be lethal, basically.
Yeah, exactly. Yeah. It's like and usually these like can stay undetected for several years. Sometimes people just randomly find that because they're imaging something else, and suddenly they discover that there's like this huge bulge somewhere in the body. And then the big question is like, how dangerous is that? Is that something we need to do surgery on? The surgery itself is also dangerous, or can we leave that and it will be okay? And aneurysms are actually something we will do an example on later. We don't fully resolve an aneurysm in 3D, but we will make aneurysms rupture today. Another common application is that drastically changes the load on a vessel is if you do a bypass anywhere in the body. So for example, that's just very broadly speaking, a blood vessel is blocked somewhere. So there's two general kinds of blood vessels, arteries and veins. Arteries transport oxygenated blood into the body, and then veins bring it back to the heart, the deoxygenated blood. And so what people often do is, or not people, surgeons, they take veins and use them as a replacement for a blocked artery. Can anybody think of why that can be a problem if I take a vein and say this vein now works as an artery? Yeah?
Because I imagine has lower pressure because it's only flowing back. So
Yeah, that's exactly it. Yeah, might also have different flow conditions, but that pressure mismatch, that's a huge problem. But it's still sometimes like it's still a very good choice, but it can lead to other problems. Yeah. And in the end, yeah, all of the cardiovascular system is basically like a pump with pipes. And so it makes sense to study how do different mechanical conditions alter these pipes. And here we are always like looking into like more longer term changes. Right? We're not looking into, I mean, obviously part of that is like the elasticity of the blood vessels that we also care about, but we are really like looking into how can we model long-term changes. How if I take that vein and use it as an artery and like an overpressure it, how does that change over a longer time scale? And the concept for doing that that we're going to use today is so-called mechanical homeostasis. So very roughly speaking, you have like some state here, and like in health, it just like fluctuates around a set point over time. Can you think of things in the body that are regulated by a homeostatic mechanism? What in your body more or less stays constant even though like other maybe conditions change? Yeah?
Temperature?
Yeah, I'd say we had a very good example. Yeah, temperature. What happens? How does your body regulate temperature?
You sweat and you get
Yeah. Yeah. Yeah, if you get hot, we sweat because the body tries. So in this case, this here would be temperature, and this would be, I don't know, 37 degrees maybe. It's never going to be exactly 37 degrees. Like might go up a little bit, might go down a little bit, but the body tries to maintain it. Another one. Blood pressure, okay. pH, yeah. Could also say glucose level in the blood. There's like a very specific disease where this does not work, where it does not return back to a homeostatic level. Does anybody know what? Yeah, diabetes, yeah. Somehow, I'm not an expert on this, but like somehow the body does not maintain this homeostatic condition for blood glucose, so you have to intervene like from the outside to like restore to that level. And same as with temperature, you perturb it, and if this homeostatic mechanism works, this perturbation should somehow over time go back to like the set point. So like here, I don't know, we go outside, it gets warm, we start sweating, body temperature goes back down. But in this context, there's also a so-called mechanical homeostasis. And so the idea behind that is that living tissue has a preferred mechanical state. We'll talk about later what that means, like how we can quantify that mechanical state. But very broadly speaking, different tissues have different preferred mechanical states that they like to maintain. So if you perturb them, they will try to come back to them. Doesn't mean they always succeed. So this is the next slide. So this, for example, could be that the tissue, we perturb it in some way, and it manages to go back to a different set point. So it stabilizes, but it didn't like specifically return to the previous set point. Or maybe we perturbed it in such a way that it's unable to return to any set point. It just keeps diverging, which means, so you could call this more adaptive homeostasis. So here this mechanism finds a new equilibrium. In this case, it didn't. Yeah. Where would we, yeah, so in case of the aneurysm, going back to that, we could quantify that in an aneurysm that just grows a little bit and then stays stable. Maybe the body found like a new mechanical homeostasis, and then the one which just keeps ballooning and eventually rupturing. Maybe something got disturbed so much that the tissue cannot find like a new equilibrium. It just keeps adapting and growing, but it will never return to that set point. We'll also look at these a little bit and like try to quantify those two cases. Yeah. Any questions so far? Pretty generic so far, but I think we'll dive more into the details. And so like one way this is more like an electrical engineering approach to like show this homeostatic system is to show it as this sort of like feedback loop. So in the beginning here we have a mechanical stimulus, for example, pressure, flow, that gives us our mechanical state. Then this state is sensed by something, so there's like some cells that can sense biomechanics. Then we have a set point, that's what the cells prefer. We can subtract the two and get a deviation. And then we have like some system that like tries to minimize these deviations. The system has like some gains, so like how much these deviations affect the system, and it has rates, like how quickly these deviations are taken up by the system. And at the end, we have some biological response. So some new tissue is added, tissue is removed, and then this is being fed back into the state, and then like this whole loop continues. And so in health, Ideally, this is like a negative feedback loop, like it's stable. It's like we perturb it a little bit, it goes back. But yeah, there's various things how this can be disturbed. Yeah, can you think of a way how could we damage the system? Like how could we potentially cause the system to become unstable?
The sensor doesn't work.
Yeah, if the sensor doesn't work, there's no way we can really adapt to the changes in like an adaptive way. So yeah, if the sensor doesn't work or doesn't work to some extent, this can easily become like a positive feedback loop. So maybe again, going back to the example of diabetes, like if I have nothing in my body that can accurately sense blood glucose level, there's no way I can accurately adjust it. And so that's why people with diabetes like externally need to measure the level of glucose and then adjust. Do I need to lower it or do I need to make it higher? Because this sensor does not work as it should. Yeah. And yeah, same in the context of mechanical homeostasis. Okay, and so today we will look at a very idealized blood vessel. Yeah, so hopefully everybody can see there's a prime example of a healthy blood vessel. So in blue, there's supposed to be the vessel wall, and this red is supposed to be the blood flow. And in general, we look into two different loads. So on one end, we have the blood pressure that is responsible for like the circumferential stress or the hoop stress that's going out of plane. And then because of the flow, we also have a wall shear stress. So it's basically just like the frictional force, the viscosity of the fluid is causing like a shear force, sorry, I should not say force, shear stress on the blood vessel. What is interesting specifically in blood vessels is these are very different in their magnitude. So typically the circumferential stress is on the order of like a couple of 100 kilopascals, but this wall shear stress is only on the order of like a couple of pascals. So these are like 5 orders of magnitude difference between these two different stresses. It's like mechanically, the vessel wouldn't really be affected much by the wall shear stress, but does anybody know how is the wall? Yeah, okay, I know this. Some people know for sure. Why is the wall shear stress important? Oh, you have an idea? Yeah.
You were talking about the microstructure, maybe that.
Yeah. There's some.
That small scale. So
Yeah. There's some microstructure. What is it?
And endothelial cells as well on the,
Yeah.
on the cell wall.
Yeah.
Lumen, they can sense the blood flowing and communicate with small muscle cells and cause constriction.
Yeah.
Coagulation.
Yeah. Exactly. Yeah. So you can think of like sort of like a Teflon liner. So that, like as you have in your frying pan, there's like a layer that makes the blood run smoothly over the blood vessel. That's the endothelium, and the endothelium can sense the wall shear stress. So you have sensors here, and that information is being brought to the rest of the blood vessel. And from these two inputs, you can compute the circumferential pressure. So this is just the law of Laplace. Jay always points out, he's talking about this is not an approximation. This is just the balance of linear momentum. So if you just cut the blood vessel in half and do a balance of linear momentum, assuming that the stress is constant, or assuming this is like some mean stress, this here is not an approximation. Of course, the actual approximation that you could make is assuming that the stress is constant over the thickness of the vessel, and which would be a thin-walled vessel. But yeah, this is just the balance of momentum here. And then under certain assumptions, steady-state flow through a straight pipe with the Hagen-Poiseuille equations, you can derive the wall shear stress. And you can see that the circumferential stress only depends on pressure, radius, and thickness. And the wall shear stress depends on flow rate. Does anybody know what the mu is in this formula? Yeah, that's the blood viscosity. So higher viscosity, higher wall shear stress. And then we have the third power of the inner radius. So a little quiz. If the pressure doubles, how does the thickness of the blood vessel change? If you double the pressure and we assume that the circumferential stress stays the same, We don't want to change the circumferential stress. So if I double the blood pressure, how does the wall thickness have to change? Thickness is H.
What is A?
Is the radius.
So it's a function of A.
And so the radius stays the same. The pressure doubles. How much does the thickness have to double for the circumferential stress to stay the same? It also needs to double, yeah. So if this doubles, this also needs to double, so it cancels out. Yeah, so basically, so that means the thickness is kind of linear in pressure. This is an example for a paper where they artificially increased the blood pressure of a wall, of a vessel, and then, yeah, the vessel wall thickens. The other way, what if we were to increase the flow rate by a factor of 8? So here's the wall shear stress, here is the flow rate, and here's the viscosity. Viscosity stays the same. And here we have the radius to the third power. And we want the wall shear stress to be the same. It doubles, yeah. Yeah, someone must have chosen a power of 3. Yeah, right. So if we increase the flow 8-fold, the radius only doubles to make up for that. And so this is another example. I think those are the two carotid arteries, and like on one side, they artificially increased the flow rate, and then like initially they were the same size. They increased the flow rate on one side, and then, yeah, or actually they decreased it on the other side. And then, yeah, you have a change in diameter, but you do not have a change in the thickness of the vessel. And those, I would say, those are like the two basic adaptation mechanisms. Or those are the two loads. We have pressure and we have flow. We can extract two biological or like mechanical quantities, the circumferential stress, sometimes we also call it the intramural stress, like the wall stress and the wall shear stress. And then we have two distinct adaptation mechanisms. If I increase the pressure, that usually changes the thickness of the vessel. If I increase the flow, that changes the radius of the vessel. Yeah. Questions so far? So now we already, I guess if you left now, hopefully you already have like some takeaway, as if the blood vessel strives to maintain wall shear stress and circumferential stress, you already know how these adapt over time. Okay, so now we're going to look a little bit into finite strain. So that just means like a short introduction into the theory of deforming solids. And for that, yeah, usually when I teach, so I teach a class about that, usually I have a potato, because for some reason, whenever you teach continuum mechanics, you must have a potato. I don't know how that originated, but yeah, this is the continuum potato. So this is the reference configuration, and this is the deformed configuration. And so typically the reference configuration is denoted by an uppercase letter. So X is just a point in the reference configuration. Lowercase x is a point in the current configuration. And like in between, we have a deformation. So the deformation just means, what do I do with a point uppercase x? Where do I put it to the point lowercase x? That's the deformation. Just tells me where do points go. And that's what I asked in the beginning, if people know what a deformation gradient is. So here it is. That's the deformation gradient. The deformation gradient tells me how does an infinitesimally small line element, uppercase dx, how does that get mapped into the lowercase dx? And it can be stretched. I can stretch it. I can just make it longer. And like I can reorient it. And the deformation gradient tells me exactly how I'm doing that. And yeah, the deformation gradient doesn't have to be constant. Like it can change everywhere in my body. It can have a different deformation gradient. It just tells me if I'm at any point uppercase x and I take a line element, how does that line element get stretched and rotated in the current configuration? Can anybody think of like a couple of special deformation gradients? What if the deformation gradient is the identity? What motion is that? Or what deformation is that? Rigid body motion, yeah, almost. Rigid body what? Rigid body translation, yeah. So if you only, yeah, I should have brought a potato. Let's use one of these. Yeah, this is going to be a mess. But if I only move it, nothing actually deforms, then the deformation gradient is the identity. What other special cases can you think of? Rigid body translation? I can stretch it. Yeah, so pure rotation. In this case, the deformation gradient would just be like a rotation matrix around however I'm rotating it. Yeah, we also made.
Deformation like on the radius or
Yeah, so if, yeah, it can just be like uniaxial stretch in one dimension, that also works. In general, it's just a combination of, I'm not going to put this back, it's just going to be a combination of all of these. So this is the 3D case. And for the next couple of slides, they already find mistakes on the first slide. If you do, please let me know. So we're going to look into the 3D theory, but we also often going to look at it just from the perspective of this cylinder. Yeah, which in this case, the deformation is just given by lambda. That tells us how the radius changes, which corresponds, because we also assume that it's incompressible, corresponds to the circumferential stretch. Yeah, so in 3D, deformation gradient, and in 0D, in this like simplified model, we just have lambda. Like our whole deformation from here to here is just given by this lambda. If lambda is greater than 1, we stretch it, like in this case. If lambda is smaller than 1, we shrink it. If lambda is 1, nothing, no deformation happens. And to compute the deformation gradient, I mean, it's kind of in the name. We take the gradient of the deformation. So we compute how does this deformation mapping, so if I map from the reference configuration to the current configuration, how does that map change spatially? That's the deformation gradient. We can take the determinant of the deformation gradient, that gives us the volume change. So if the determinant of the deformation gradient is perfectly 1, no volume changes. Which of the earlier special cases didn't have a volume change? Yeah?
rotation and translation.
Yeah, exactly. Those would be 2 cases where this is perfectly 1. But there's also the case when you go from, imagine, so typically things with fluid have, that like incompressible fluid have a deformation gradient of 1. Think of you fill a balloon with water, and then you deform it. You can deform it in various ways, but the volume stays the same. Even those deformations also have a determinant of 1, even though they're not rigid body motions. And then, yeah, for our scalar, we just divide the current length over the reference length, and that's our scalar deformation. And then, in continuum mechanics, people don't like using the deformation gradient directly, and there's a reason for that, because the deformation gradient contains rigid body rotation. But if you imagine, you want to, let's say, forget about like everything biological, let's say you just want to compute how much stretch is like in a piece of steel. For that, it's not really relevant if I stretch the steel and then like rotate it by 90 degrees. But that's something that would be contained in the deformation gradient. And there's like a very easy trick to get rid of the rotation part of the deformation gradient. So if we assume the deformation is the product of a pure rigid body rotation and a stretch, then we can write it this way. So we can write F transpose F, then is R times U transpose, which is U transpose R transpose. Oh, there's a transpose too much. Okay, this is wrong. So it should just be U transpose, R, and U. And if you compute, since the rotation, yeah, what happens to R transpose R if R is a rotation? Yeah, it's the identity. So this appears, and at the end you just have the square of the stretch matrix. So this is why people like to use C instead of F. So just F transpose F, and then C is called the right Cauchy-Green deformation tensor, and it just includes stretch. So we get rid of all rigid body translation. Why? And then, yeah, from this C, we compute the Green-Lagrange strain E. Does anybody have an idea why do we subtract the identity from the C? Why would one do that? Like, why do we prefer this as a strain and not this one? Yeah?
So that if there's no stretching, it's 0?
Yeah, exactly. Yeah, that's the whole reason. Yeah. So if there's no deformation, deformation gradient is 1. So F transpose F is also identity. And so if we subtract the identity, it's just 0 at 0. The 1/2 is a little bit more complicated, but it's no, it's not complicated. It's related to the square here. So this is the square of the stretch, and we divide by 2. So if we linearize the stretch, it still has a slope of 1. That's the whole reason. There's technically you could produce any other strain metrics. You could like use the 4th power of the stretch. You just have to make sure that here you divide by 4. But yeah, so now we know what stretch is, and we now defined a strain measure. So this is the green Lagrange strain. And we can do the same in our scalar cylinder. So in this case, the right Cauchy green tensor is just lambda squared, and then the green Lagrange strain is 1/2 lambda squared minus 1. Yeah. So it's like very, very brief crash course in continuum mechanics, but yeah.
Could you please say again the meanings of the individual matrices?
Mm-hmm. Yeah, okay. No, good point. So F is the deformation gradient. It tells us how does this deformation map change locally? How does it get stretched and rotated? And as with any second order tensor, like let's say any matrix, you can decompose it into a pure rotation and some other part. And in this case, we can decompose it into pure rotation and a pure stretch part. And just by definition, we want to compute, let's say we want to compute something that's F transpose F. The rotation cancels out, and you're only left with the stretch. So now you have something that's invariant to rigid body rotation. So if I stretch something and then rotate it a bunch, the rotation doesn't matter. And then as the final step, we take this stretch part and subtract the identity. So just so if there's no deformation, we don't have any strain. And then we divide by 1/2. So if we were to linearize it, it's a slope of 1. Yeah. Like leaving out some details, obviously these are like second order tensors, like not clear like how we take a derivative of this, but even like in the scalar case, you would see that around lambda equals 1, it has a slope of 1. That's why we normalize with this 1/2. Yeah. Does that make sense? Yeah, okay, cool. Yeah, then we can work with that to compute stresses. Today, the only stresses that we look at are stresses from a so-called strain energy density function. You can think of this as like a potential. You've all seen this before, probably in high school physics, if you looked at a spring. Does anybody know what the stored elastic deformation energy of a spring is? If I have like a linear spring with stiffness K, and I deform the spring, let's say, by delta x, what is the elastic energy that's stored in the spring?
1/2.
Yeah. Oh, yeah.
Squared of the delta.
Yeah, that's it. 1/2 spring stiffness times delta x squared. And this is something similar. So the W is the elastic energy that's stored in the tissue. That's a modeling assumption, like no real tissue technically behaves like that, but it's a really good model. And then people do experiments and like come up with actual forms of like how should W change with deformation. But in very general, it just means all the elastic energy is stored in and is described with this W. What does that mean for the tissue? What does that mean for the deformation? If I can describe its deformation energy in a potential, what sort of materials exclude that? Or what materials can I not model with that? Rigid, I think rigid materials, would not work, yeah. But fluid? Why not fluid?
Because there's like dissipation.
Yes, dissipate. Yeah, so that's the big issue. Yeah, this cannot handle dissipation. So this means all the elastic energy is stored and you can retrieve it. There's no dissipation. So there's no viscosity, for example. But it's a very good model for many materials. And it's like, so whenever we're going to use materials today, they were all going to be in this form. And those materials are called hyperelastic. And the nice thing is for hyperelastic materials, if you know what W is, you can compute the stresses if you take the derivative of W with respect to the right Cauchy-Green tensor that we introduced earlier. Same works for the spring. If we know the potential of the spring is like 1/2 k delta x squared, how can I get the force of the spring?
You take the derivative of the energy to get the delta x.
Yeah, that's it. Yeah. Yeah. And then it just becomes k times delta x is the force of the spring. So I would say this is like the 1D analog of this. You take the derivative of the potential with respect to the deformation, you get a stress. One thing that we have to be careful with is so I wrote here, stress is force per area. It's true, but in 3D, stress, first of all, is a second order tensor. It's not just a scalar. And then the tricky thing is, what force do you use and what area do you use? So there is no one stress measure. And here there's two shown. So the uppercase S is called the second Pfaller-Kirchhoff stress that measures force in the reference configuration and area in the reference configuration. The Cauchy stress, that's sometimes also called like the real or true stress, measures the force and the area in the deformed configuration. So that's might be a little bit confusing. There's just two different ways of measuring the stress. And there is no right or wrong. It just matters sometimes some people would prefer one or the other. For the people who are doing experiments, what stress do you prefer? Is there
We work with Cauchy.
Cauchy? Okay.
Yeah.
Not first Pfaller-Kirchhoff?
And that's an experiment.
Oh, so yeah, okay, right, yeah.
With inflations,
Yeah.
typically, you calculate to Cauchy
Yeah.
using the plus law.
Okay,
But indeed, if you have a planar test, then first Pfaller-Kirchhoff
okay, okay.
can come in. So first Pfaller-Kirchhoff is another one that's not on the slide here.
That's not on the
It's
slide, yeah.
Sort of in the middle of those two.
Yeah, so for the first Pfaller-Kirchhoff stress, you take the current force and divide it by the reference area. And sometimes that's nice, because why could it be nice that we normalize by the reference area? If you imagine like a tensile test, you're pulling on something, you can measure it beforehand, like it doesn't change. But you can measure the current force with your apparatus or something. So just to say there are different stress measures. I think for the rest of today, I think we're all going to look into the Cauchy stress. But the one derived from the strain energy function is the second Pfaller-Kirchhoff stress. And then you left and right multiply some deformation gradients onto it, and then you get the Cauchy stress. There's some bits missing here why it's exactly that. But yeah, this is a way just to convert between different stresses. And obviously we can do the same for our scalar stress metric. Okay, now almost done all of the continuum mechanics. So now these are two examples of what these strain energy density functions look like. There's two materials that are important for vascular tissue. There's more, but these are, I think, the most common ones. There's a neo-Hookean material, and then there's also a Fung type material. What they do is they take the deformation gradient, or C, and then compute invariance, and then just compute a strain energy with respect to the invariant. We probably don't need to go into detail why they look like that, but maybe one question for that would be, what properties would we expect from the strain energy density function? How should it depend on deformation? So a couple, I would say there's two things that would make sense. Yeah? Should be monotonic, yeah? Or even more broadly speaking, if you take it one step back from monotonic, a weaker but more broad requirement. If I put more stretch into the strain energy, what should the energy do?
Some sort of continuity?
Even more fundamental than that. I mean, it should ideally also be continuous, but it should just go up. Like the more I deform it, the more, I guess that would be monotonous. Yeah, it should increase with stretch, but you're right, yeah. Technically, you could put, no. Monotonous is, I think, is the right term. What's the other property? What if I don't put in any stretch? What should the strain energy function be? Should be 0, yeah. So in this case, you can see that. So I1 is also sometimes called the first invariant of C. What is C if, does anybody remember? What is C if there's no deformation? It's the identity, yeah. What is the trace of the identity in 3 dimensions? 3. And so here is I1 minus 3, so it normalizes for, not normalizes, but like makes sure if there's no deformation, there's no strain energy. And then I4 is, people call it, it's a pseudo-invariant. It's not really an invariant of the tensor, but it's related to a fibrous direction. So often people have, especially if you have anisotropic materials, so they have different stiffness or different material behavior depending on in which direction you load them. Then you could model, if you have like a fiber in your material, you could model the strain energy with a deformation only in that fiber direction. And then often people use this like I4 as a pseudo-invariant. So these are 2 very specific material models that we use a lot in the context of cardiovascular mechanics. But there are many more out there, and obviously you can combine these and you can fit these parameters to experiments, but this is like, I would say, the 2 most basic ones that we use. Questions for so far for the continuum mechanics?
Just for the sake of the timeline, like these models go back to the 50s, 60s?
That's a good question. So Fang, I think Jay did his postdoc with Fang. No, not Fang. Never mind. No, I don't think so. Maybe it's like 60s, 70s, something like that.
Just passed away.
Yeah.
Recently.
Yeah.
That was with Jay.
Yeah, 50s, 60s, 70s. Yeah. But you can come up with your own model. I think these are still popular because they are super easy and yet still are able to characterize materials. Like often like soft biological materials, but I think for rubber, people also use these kinds of strain energy functions. Yeah.
What are those C1 and C2?
These are the material constants. Yeah, I should have said that. These are the material constants. So like the C's are the ones you would actually fit to the experiment. So this would be the stiffness. And here you have 2 stiffness parameters. This one is like, this thing has a unit of stress. So this also would have a unit of stress, and then C2 is just an exponent. So C2 controls. So this is does this material here, does it get stiffer or softer with deformation? What do you think? The more I deform it, do I have to put in more or less energy? Yeah, why more?
Because it has the reflex to go back.
Yeah, but it could also be like, for example, the spring is perfectly linear, right? In the spring, if I double the distance, I also double the force. But in this case, I have another relationship of 4, like, yeah? Yeah, it's exponential. Yeah, it's an exponential function. So like the more you pull on it, the more force you have to use. And the C2 controls like how steeply does it rise with deformation. Yeah. Yeah. But good question. More questions so far?
The other slide, there was an equality between a partial derivative and a total derivative.
An equality between the total derivatives. Yeah, this is just saying, I mean, this only depends on lambda. I don't think it makes a difference here. So this is saying like the derivative with respect to c, but here c depends on lambda. So I think the only reason why there's a total, there is no more things to differentiate with respect to. Yeah. Well spotted. Okay. Other questions? Okay. Okay, so this was like the crash course on continuum mechanics. So now I got like a brief overview how like of some tools we use to describe deformation in bodies. And so now we actually get to the first growth theory of the day, and that is kinematic growth. And so what you do, that can be explained very simply. What we do is we multiplicatively split up the deformation gradient. So we take the deformation gradient, as introduced before, and we say it's the product of two deformation gradients. It's the product of an elastic deformation gradient and a growth deformation gradient. And only the elastic part is the one that stores deformation energy. The growth part we will look at in a second. But yeah, we split these up. Obviously, for our scalar problem, that just means our total stretch is a product of an elastic stretch and an inelastic growth stretch. And this was introduced in 1994 by Andrew McCulloch's group at UC San Diego. And this had been used before to model plasticity in metals. So like some people use that to model, if you deform a metal past like its yield stress, then you have plastic deformation, and that inelastic plastic part would go into the growth part, and that whatever goes back after you remove your load is stored in the elastic part. And there's also this like nice visualization that you see whenever this model is used. So now we have three configurations. Before we had just had two configurations. We had a reference configuration and a current configuration. And now we have this intermediate configuration. And this intermediate configuration, people call that incompatible. So think of it as you take a reference configuration and like you cut it into many, many small pieces. So now here it's 4 pieces, but technically you have to cut it into an infinite amount of infinitesimally small pieces. And then you take each of these pieces and you grow them individually. But what can happen if you, I'm not going to do it, but if I cut this up into like many small pieces and they all grow individually, they might overlap or there might be a gap because they're all growing individually. But this is why this is called an incompatible grown configuration. The pieces don't belong together anymore. That's why, but in the end, that's not what we want to model, right? That's why we have this elastic part of the deformation gradient, which restores this compatibility. So like it takes all these pieces that are now like overlapping and have like gaps in between them, and like it glues them back together. And this gluing back together will cause like a certain amount of stress, which is sometimes called residual stress. But those two together then yields the current configuration. It's this combination of growing it locally and then gluing it back together in these like 2 steps. Does that make sense? So it's not something that actually happens. It's just like a modeling assumption that at every position inside the reference configuration, it can grow independently of the rest of the tissue, and then we sort of use this elastic part to like stitch it all back together. That's, yeah?
The other way, like with like elastic stress first, then throw it later. Like something.
So you're always doing both at the same time. So like the way it actually works when you compute something, you prescribe this part, like you have like some law how it grows, or you can even like just prescribe how it grows, and then from that you derive how much the elastic part is. Yeah, so like this is typically either prescribed or like dependent on like some stress or like some strain, whatever you want, and then you know what the grown part is, and then you compute with that grown part and like whatever deformation you're applying on the outside to your body, what does the elastic part have to be. But you cannot directly prescribe the elastic part. I guess maybe we could do like inverse one, say like, okay, this is the elastic part, how did it need to grow to do that? But typically, when you apply it, you typically apply it this direction. Like this, you figure this out first and then that part. That's good point. Do you have other questions so far for our first growth model? Yeah?
Before, I think F was seen also as the derivative of the mapping
Mm-hmm.
to states.
Yeah.
Can you think of it like now becoming a composition of two different mappings, each one?
I think you lose that property. I don't think you can go. That's a good question.
I mean, I don't know.
In the
what
end,
is the
yeah.
purpose of this, but maybe that can be also helped with something.
Yeah. Yeah, that's a good point. I think you problem with taking the derivative is not like this can be technically could be discontinuous. Like only like this whole thing together is still this is still a continuum, but this like virtual configuration in between technically doesn't have to be a continuum. So like this whole taking the derivative of the deformation map, technically that's not defined here anymore. Yeah. And this like as I had like this is just like something we imagine exists, but it does not really. It's it's just a model assumption basically. Yeah. Okay. More questions?
Is there a point why we decompose it like this? Like, is there a particular reason?
It's very easy to do.
Does it make things easier later on?
Yes, much easier. Yeah. And you will see why this is like we will do this and then something that's not as easy, and sometimes it gives you the same result, and then you have to decide for yourself which one you want to do. But this is conceptually this is the easiest thing you can do to make something grow, I would say. Yeah. That's also why we're doing it first, before introducing more complicated things. Yeah, it's like the way it typically works is that you prescribe a growth tensor, like the FG. You typically have something in mind what it should look like. So often, for example, for the heart, what people often assume is there's like a fiber direction in the heart, like there's like some preferred direction, and then we say along that direction we want to like grow. So in the end, the growth deformation gradient has on the diagonal 1, 1, and then this theta, which is the amount of growth along that one direction. But you could also say like we could combine different directions. You can define these directions in like some local coordinate system, whatever you want. But typically, you already know, okay, it will grow in this direction. Obviously, in the scalar, like in the tube example, there is only one direction in which it can grow. And in this case, the theta also corresponds to like the increase in mass. And it also, in this case, like corresponds to the determinant of the growth deformation gradient. So if you take the determinant of that, it's just theta, because it will just describe something that describes a deformation, just in this case grows along the z direction. Yeah. So if I have the cookie and let's say this would be the z direction, then this deformation gradient would just make this blow up in this direction. And then you need to combine that. You somehow need to know what theta is. The easiest thing would just be prescribe it over time, but you can also define like some evolution laws. You can say, I define this like ordinary differential equation where I say the time derivative of theta depends on this like gain parameter times theta itself times this here. So this compares a certain mean stress to a certain homeostatic set point. So now we're getting back to this like idea of homeostasis. So if we compare the current stress to a set point and subtract 1 from it, we can define how much theta grows or shrinks. And so what happens if you actually like solve this ODE, if sigma bar is greater than sigma bar h, this here is positive, so we get some d theta dt that's bigger, so it will grow. If it's perfectly equal, if sigma bar is perfectly equal to sigma bar h, then we are in homeostasis, because then this whole side is 0, and d theta dt is 0, nothing will change. Or if sigma bar is smaller than sigma bar h, then yeah, we have something negative here, and then the theta will shrink. So this is like the easiest way. This is like a simple growth law that will make sure, oh yeah, what does this do? Like whenever I perturb it, what will the system do over time? Like if you have this ODE, I plug in, I initialize it with any sigma bar. What should it do over time?
Sigma bar goes to sigma bar h.
Yeah, ideally it should go back to sigma bar h. Yeah.
The theta or the sigma bar?
It's a good point. The theta should change the whole system in a way that it goes back to sigma bar h. Yeah. If you think of it, what did we say? Like we had the increase in pressure that caused an increase in wall thickness. So if the pressure is higher than the homeostatic set point, then this is greater than 1, then we have growth. What happens with the stress when the vessel grows? Like if I add more mass, what would happen? If you think back to Laplace's law, if we add more mass and the vessel wall becomes thicker, what happens to the stress or the circumferential stress in that vessel?
Goes down again.
It should go down again. And if the stress goes down again, then the increase in mass should also go down. So technically, we now have all the ingredients here for like a very fundamental negative feedback loop. If I make the stress higher, I produce more mass, our wall would get thicker, stresses would go down, and same if the stresses would decrease below the homeostatic level, I would move mass away, the thickness would go down, like it would be thinner, and then the stresses would go back up. So ideally, those two together, how we compute the stresses and how the growth evolves over time, should return this back to homeostasis. I think, oh yeah?
Question. In a way, can you think of theta as the sensor?
Can we think of theta as the sensor? It's tricky because it's also the response, kind of. It's both, I would say it's like 2 in 1. I would say the sensor is more this part here. This is the sensor. Or in 3D, in 3D the question would be, what stress do we use? Like how do we get from a stress tensor to a sigma bar? But in our simple case, we just have circumferential stress. But I guess this would be the sensor. How does the current circumferential stress compare to the homeostatic one? And then this is the theta, I would say, is like the response. Like this is my biological signal. In this case, my biological signal is produce more mass. Yeah, good question. I would go further and introduce the next theory of growth, and this time also remodeling. So the kinematic growth theory, we can summarize. We saw it will always, given we defined it this way, it will always return to homeostasis. And technically, it only models growth. So it does not involve remodeling, strictly speaking. If you go back to like the very first slide, we said growth is a change in mass. That's what we're simulating here. We're not concerned about the microstructure. We're not really like modeling what is happening in that tissue. It doesn't get like stiffer. There's like no reorientation of the tissue or anything. It's just growing. We're just inflating it in a pre-described direction. The other thing is, what we are also sort of like sweeping under the rug a little bit. I mean, always sweeping things under the rug. We're modeling things. They're never exact. But another thing that's not included in this model is we're just pretending the tissue is like one homogeneous thing. There's just like one block of tissue. And we will see later, one, that's not the case. And there are other models that take into account that the tissue actually consists of like different constituents. And which brings us to our next model, which is the constrained mixture model. So this was developed by Humphrey and Rajagopal in 2001, and Jay wrote, or 2002, and Jay wrote this nice paper, Constrained Mixture Modeling, 20 years after. It's on the website, and it's also like at the literature in the reference at the end of this presentation. I highly recommend, if you're interested in the constraint mixture model, look at the 20 years after paper that has like all the key equations you need. This is also like what I sort of used as a blueprint of how I designed the next couple of slides. And it also has like a nice summary of how this model was used. I don't know where Bart, maybe some of these should be you. And yeah, aneurysms, aortic aging, aneurysms, inflammation, tortuosity, Benker.
Yeah, my main paper is after 2021.
Oh, okay.
Aging and so.
Yeah.
No, it's too.
Yeah. Yeah, just after that, okay. And so this is the core idea. So this is always, whenever you see constraint mixture theory, it always comes back to this figure. And there's a lot going on here, but I will walk you through it piece by piece. And so one big difference to what we looked at before is that there are different constituents. And so these are different parts of the tissue. There are many different constituents. We only care about the most structurally relevant ones. So like we care about the ones that can actually mechanically like bear loads. But in general, these are different parts of the tissue, and like together, they all get mixed together. In the end, we don't like resolve individual types of cells. We just assume there's still like some mixture, but these are like the different ingredients. I guess if you like were baking a cake, you would put in the milk, you put in the sugar, you put in the flour, and then in the end you make a mixture. But we take into account that this cake batter consists of like different ingredients. And so those are the ingredients going in. And then I guess this would be the cake batter at different time points. And so what the constraint mixture model does is it tracks how this mixture evolves over time, and it tracks for every constituent when it was added and when it was removed. So these tissue constituents, they can be added into the tissue, and they also degrade over time. So they also get removed. Because it turns out, like in the body, there's like always a constant turnover of cells. It's not like we're born with cells and then that's it until we die, but most of the cells continuously turn over and get renewed. Does anybody know, in the cardiovascular context, tissue that does not get renewed? It's also the one fact that keeps all cardiologists in business. It's one thing that does not get renewed, or at least very, very slowly. Elastin? Elastin, yes. And the heart muscle cells also don't get renewed. So this is why whenever you do damage to the heart muscle, that's permanent. And that's why heart disease is usually very severe. And like, how should I say, like, yeah, the heart itself doesn't repair. Like the heart muscle cells do not get renewed as compared to like skin scales. If I cut myself in the finger, like it will be repaired over time. If you cut into the heart, like it will have that cut forever. But yeah, so most cells are continuously, new cells are being deposited and old cells are being removed. And that process is called turnover. And in the constraint mixture model, you're tracking all of that. You're tracking at which point did I add something to the mixture and when did I remove it? And then, so you have these sort of like in vivo configurations that evolve over time. Where it gets a little bit spicy is that we're dealing with two different times, and none of them is called T. One of them is called S, and the other one is called tau. S is the current time. Tau is any time between the current time and 0. So tau is like at any past time point, when did we add or remove something? Those are like all the different times tau, and S is the one we're currently at. And there are a couple of tensors in here. So maybe start with this one here. This G is the pre-stretch. This is like the preferred stretch that every constituent has. And so whenever we are putting a new constituent into the mixture, we're putting it in with a certain pre-stretch G. So So not just like as an, I don't know if this is a good analogy, but like if you're baking a cake, it's just like pouring in, I guess this is not even a solid, just pouring in milk or something. But in this case, all of these constituents are pre-stretched. The only good example I found is, has anybody seen those videos where people put rubber bands around a melon and you keep adding them, and somewhere melon explodes, everything blows up. But the rubber bands, I think, are a good example for these tissue constituents, because you don't just take the rubber band and like throw it onto the melon. Like, what do? Like, you take it and like you pre-stretch it and then you put it in. And this is the same as with these constituents. You take them in the natural configuration, you pre-stretch them with G, and then you release them into the tissue. And that means by putting them in, you can like change the the mechanical configuration of the mixture. And also when they get removed at their current stretch. So that means if I'm constantly removing things and I'm adding new things in a pre-stretched configuration, I can also use that to restore homeostasis. So if you think back of this like hypertension example where we increase the blood pressure in the blood vessel, if the blood pressure goes up, I can like remove old constituents within the current configuration, and I can like pre-stretch new ones and like put them in. And like depending on how many I remove or how many new ones that are already pre-stretched, I can like try to balance it and like bring it back to homeostasis. Does that make sense? So this is like a key thing. One, there are several constituents and all of them have a certain pre-stretch. And so now where things get a little bit spicy, no, it's not really spicy, but like it gets a little bit annoying is how do we know how each of these constituents deform? And there's this like famous deformation gradient that has 3 different indices. Alpha are the constituents, so all these alphas, these are different constituents. N is the natural configuration. Tau is the time when the constituent got added, and S is the current time. So this thing tells me how much is constituent alpha that got added at time tau, how much is it stretched now at time S? Might not be the same as tau because it moves with the mixture. Just because I put it in with a certain pre-stretch doesn't mean it still has that. Like it can deform elastically and other constituents could have been added and the whole thing deformed. So like this can change. Question? Or?
So Fn tau of tau is J alpha of tau, or?
How do we compute that?
No, how do we compute that? We want to calculate that because we introduced it at tau and we want to see how it evolves at time.
Yeah, right.
Initially at time tau, what's the value?
Yeah, that's a good point. Why do we even need that is if we want to know what stress it has. Because this deformation gradient here, that's the one, that deformation gradient tells me how was this constituent deformed. And so whenever we want to compute a stress and use that strain energy function we introduced earlier, then we need this deformation gradient. Like this is the only one that actually tells me how was this thing deformed from its natural configuration. If you think back to this like melon example, we take the rubber band, we pre-stretch it, and then we let it go and add it into the mixture, but then at a later time, the melon could have already deformed. Like it's probably not exactly in that stretch I put it in with, and that's why we need this one just to know how much has it been deformed, and then so we can calculate what's the strain energy and what's the stress that this rubber band has now. And so how do we get this? Well, there is a little bit of a detour. So we know what this is. This people determine in experiments. They know what is that preferred stretch that the constituent wants. In my case, I know how much I stretched the rubber band. Then we need to know how much was this whole thing deformed at time tau when I added it. So this is this deformation gradient. If I take the inverse of that deformation gradient, I can go back to this reference configuration. And then if I take this deformation gradient here, that tells me how the whole thing is deformed currently, then that's the equivalent of this deformation here. So as long as I keep track of what was the overall deformation at all past points tau and store these deformations somewhere, I can always go back and say, oh, I added this constituent at that time tau. Let me now invert the deformation at that time and then go forward with the overall deformation at time s. And this is the same as this f tau s, or f alpha n tau s. And all of these for every constituent. So these pre-stretches are constituent specific. Every constituent, let's say I add 2 different kinds of rubber bands, a thin one and a thick one. For whatever reason, I could choose a different pre-stretch for all of them. Doesn't matter, as long as I know how that whole melon was deformed at that time. Can always go back to the beginning, and then this is also called a pull back and a push forward, and push it forward with the current deformation. All I need to do is keep track of when I added it and what was the deformation when I have added it. Yeah?
It depends on the exact form of F, but I just wonder if it happens to be a Markov-line process. So F from tau to S only depends on the difference between S and tau.
Mm-hmm. It only depends. That's a little. So it only depends on that difference, but it depends on. As we will later see, it depends on all the differences. So like, and the problem is, imagine I added something already here. It might still be present at this time point. So at every S, I need to go back through all the taus and figure out at all the previous taus when did I add something, and how, at what configuration did I add it, and how much of that is still remaining. So it's not just the difference. Yeah, so basically, at every S, we need to do like a sweep from 0 to the current S over all the different taus and check what did we add at all those past times. Going back to the melon, whenever I add a new rubber band, it also matters how many old rubber bands I already added. Maybe some already fell off or changed in some way, but like I need to track when did I add these rubber bands and what deformation have I added these. So maybe you can already sense there will be an integral over time at some point, because we need to take all those past configurations into account. And as I said, like, we track when stuff was added, and we also track when it was removed. And we will talk about like how we model, like how we decide when stuff should be added and when stuff should be removed. But in general, we just keep track of all these different configurations of the whole deformation, and we keep track of under what pre-stretch we added these things. Does that roughly make sense? Are there more questions for this? This is probably the most illustrative it gets. After that, it's more equations, less figure heavy. So if it doesn't make sense now, speak up now. But obviously, like, maybe the integrals also help. And again, the elastic deformation of every constituent is given by this arrow. And one way to compute this arrow is just going backwards, using the known deposition stretch, using the inverse of the deformation when it was added, and the forward deformation from the origin to the current time. And S is always the current time, and tau is any time between 0 and S. T is never used. I guess if you want to impose any like elastic deformation on top of that, you can use T. But for this, as far as this is concerned, the constraint mixture theory never use T. That would be too straightforward, I guess. Okay. So I talked about these constituents, and yeah, as Bart already said, like elastin is an important one. There's also collagen and smooth muscle. So typically we resolve these 3 because these are the structurally most relevant for tissue constituents. They all have a mass fraction that sums up to 1. So this just tells us how much. There's different mass fractions at different masses, but generally just tell us like how much proportionally is there of every constituent. They all have a certain pre-stretch that you can determine experimentally. They have a constitutive law, so the two we introduced earlier with the two invariants we use for these constituents. And the turnover times, like this is a very roundabout value. I think it goes like, I don't know, between like 20 or 100 days or something. And this is like the mean amount of time how long these are present. Elastin just decays so slowly that we typically just say it's constant. It doesn't renew or turn over. Yeah. But it's important that these two do turn over because that's the adaptation mechanism. If none of them would turn over, we would not have any adaptation. Yeah. I think I saw a hand or question. No? No? Okay. But yeah, so these are the ones that we will actually model. Maybe one thing. Before we talked about a homeostatic stress. Here I've talked about a pre-stretch or homeostatic stretch. We can easily convert between the two if we plug in the homeostatic stretch into the constitutive law, we get the homeostatic stress. So they're easily related. And this is the constituent-specific deformation. So this is the elastic deformation, and that's taking the deposition stretch, using the inverse of the total deformation at that time tau, and then the deformation at time s. And that gives us this individual elastic deformation. The reason why this is so we now know it's a mixture model. There's all these different constituents. Why is it the constraint mixture model? Because we assume they all deform together. So this is why it's okay to use this detour here as the equivalent of that, because they all deform at the same time. So if I know what the total deformation at time tau was, I know how all of these constituents got deformed. That's what makes it constrained. They all have, the constraint is all constituents deform together. It's not like I pull on elastin and then like collagen and smooth muscle are doing something else. It's like, no, I pull all of them at the same time. And they deform together. It doesn't mean that they're like all parallel. They can have different orientations, but they all undergo the same deformation. And then for our scalar example, it's a little bit easier. So this, instead of f, alpha, n tau of s and t, I guess we don't need this in here. We can just take, again, the deposition stretch. We divide by this total stretch at the time tau when we added the constituent, and then we multiply with the current stretch. So this is basically the 0D equivalent of this equation here. Yeah. Questions? So that roughly makes sense. Under which condition is this lambda, under which condition is this deformation gradient exactly the deposition stretch? At time tau. Yes, it is. Yeah, exactly. If I'm exactly at that, if it was added right now, then those two are the same. Yeah. Yeah.
The deformation is also the identity, and the
Yeah.
whole system does not move.
Yeah. If nothing gets moved as well, then it always stays the same. Yeah. Yeah. Nice. Okay. So now we can calculate a balance of mass. And so typically we don't work with mass, but with density. So we can write this transport equation. So again, S is time. So the change in density is the divergence of the density times the velocity, and that equals a net mass exchange. So basically, does anybody know what does this transport part here? How can I visualize that, or what does that mean for the tissue? Like, why is it not just the derivative of the density is the net mass exchange? Like, why does this additional term come in? You might have for the fluid people, you also have something very similar to Navier-Stokes equations, but it's not a. Yeah, we have.
Just guessing, no idea. Maybe because it's somehow compressible, or.
Yeah, that has to do with it. So this would just be like a flux of mass. Like if there would be mass just like flowing around on the inside, just moving around inside the body, then you would have this transport part here. But in our case, this will be 0 because all the different tissue constituents, so this is the velocity in here, I should have said, and all the different constituents have the same velocity, which is part of the constraint assumption. If they move together, they also have the same velocity, so there will not be any mass. So this divergence should always be 0. And this net mass exchange, another way of writing that, so that here it's an m bar, here it's just an m. We can just write the mass exchange as production minus removal. If they're both negative, if they're both positive, then we can write the net mass exchange as production minus removal. So if this net mass exchange is positive, we're adding stuff, we are growing. If it's negative, we are removing things. So it's just a different way of writing this.
How is this conceptually different from transport?
It's not. Yeah, we're just defining this is how we're going to model a change in mass. Okay, and so now we're getting to the first integral. Okay, so we assumed every tissue constituent has the same velocity since they move together. And instead of having a production rate and a removal rate, we have a so-called survival fraction. So this is just a function q between 0 and 1. It just tells us how much of this constituent is still remaining. If it's 1, we must have just added it because everything is there. And if it goes to 0, we completely removed it. So it just disappeared over time. And then from that, we can write the current density of constituent alpha as how much is remaining of the original constituent plus all the different, like this is why we have an integral of our tau going from 0 to s, all the different constituents that were added at a previous time tau and how much of them is still remaining today at s. So like this function m alpha tells us how much was produced at time tau, and then q of alpha of s and tau tells us if something was added at tau, how much is still present at s. And if we take that whole thing and integrate it from 0 to the current time s, then we have accounted for all the different constituents that were added at some point, and we're taking into account how much of them remains to this day at s. Does that make sense? Plus whatever was there in the beginning. Another way of writing this integral is removing this term and letting, oh yeah, maybe you figure this out. What's another way of writing this? Let's say if I don't want to specify this point 0 here, how could I modify this equation? What do I have to change about the integral? If I don't say like, well, I don't really know what that point 0 was. Let's say there's a way of writing this equation without this part here. What do I have to change in the integral to compensate for that? Yeah?
So integrating from -infinity?
Yeah, that's it, yeah. If I just let this go all the way back to the beginning of time and integrate over all of that, I don't need to specify what was there at 0. Obviously, that's not practical, so it's easier to just say, well, I knew how much there was in the beginning, and this is how much is still remaining, and then everything else, I just sum it up from time 0. But technically, we could also write it as an integral from -infinity to s.
So this is nothing but the PDE that we were used to writing just without the survival rate?
The what? what do you mean? Like related to here?
We're just integrating, right? Basically.
Yeah, we're just exactly. We're just integrating this equation. Yeah. We're saying this part is 0, and then we're integrating this over time. Yeah, that's it. That's the whole secret. And then we're writing this as production times survival. Yeah. That's a good point. Yeah, maybe that makes it easier to understand. We just took an integral. Yeah.
I guess in practice, you're always integrating at most from the point where Q becomes 0, distance in time, right? Because at some point you will
Yeah.
have lost all of your mass deposited time.
So this is a good question, because this is also, can anybody already see an issue with this theory, and like why people prefer maybe the kinematic growth, or conceptually it's much easier to do kinematic growth than this. Like, what is a big problem with that? What do I need to keep track of? The Q, yeah. Yeah, or like, or very broadly speaking, I need to track every constituent in the past because I will need it for this integral. And then at every, let's say we discretize in time, we have discrete time steps. At every new time step, I cannot do finite differences on that. I cannot just like take what we had before and add a little bit to it. I still need to re-evaluate this integral that goes over all the previous time steps. And so to your question, like, oh, can I forget them at some point? You can, but just because there is little left doesn't mean it's not relevant. What if I add something with an enormous pre-stretch, add it in, and then this slowly decays? So even though I still have like only a tiny bit remaining, it still might have a large mechanical influence. So it's tricky to say like when is the cutoff. Like obviously at some point, if you have a simulation that runs for like 5 years with a time step of a day or something, at some point you get very tired of evaluating these integrals and be like, hey, these should be decayed. Like why do I still need to take them into account? But you technically you don't know what is the mechanical influence. We wrote a paper, so Amadeus Gebauer, the PhD student in Munich I mentioned on the first slide, he developed a method to like assess can I drop old points. And so what he basically does is he removes a time point, he removes a constituent completely and looks at how much did it change the result. And if it didn't change in a significant way, he drops that time point. So like basically you're thinning out your integration points over time and you're not keeping all of them, which is like I would say like a more thorough method of saying like, okay, it's disappeared now. But people have definitely done that in the past and said like, I'm not saying like it's wrong, it's just a different like assumption. Yeah. Good point. Other questions? But yeah, this is our first integral. And this just tells us what is the total mass of that constituent. And since we're assuming like the actual density, the bulk density of the mixture does not change, this mass also corresponds to volume change. Okay, then what else do we need? We need a balance of momentum. In our case, we assume that at the time scale where this growth and remodeling happens, that happens so slowly we don't need to really take into account the acceleration of the tissue. So we can just assume that so that's basically the 3D equivalent of Newton's third law, F equals ma with A set to 0. So like it just means all forces sum up to 0, which in this finite strain theory means that the divergence of the Cauchy stress is 0. And so now, when we go back and we want to compute that Cauchy stress, so this is the same equation we had before. This is the strain energy density function. This is the right Cauchy-Green deformation tensor. This here would be the second Euler-Kirchhoff stress tensor, and then it gets transformed into Cauchy stress tensor. That's all the same. However, there is one missing part, and that is, what is that W supposed to be? Like we don't, because now it's a mixture of things. Before that, if you just have one material, we need to decide on one strain energy density function, like whatever that one material fits best. But now we have all these constituents. So it's not just one strain energy, it's like what are those individual strain energies. So next we're going to look at how do we get this like combined strain energy from the constituents. And since it's a rule of mixture, so that's nice about this kind of modeling, we can just sum them up. So the combined strain energy will be the sums of the constituent strain energies. But we still need to figure out what is the constituent strain energy. And for that, we need to figure out what is W alpha, what is the production rate, and what is like the survival function. So now we actually need to find functions for that. And so one, for the material itself, we can just assume, for W, we can just assume another strain energy as we had introduced them before. And then we actually now need to define a production rate. And the way that's typically done is defining like a base rate. So this is like if we left the tissue undisturbed, how much would there be naturally produced? And then we can add different stimuli. So we can add something that depends on circumferential stress with a gain factor. We can add something that depends on wall shear stress. And we can even add things depending on inflammation, for example, if you want to model that. So whatever it is, you can like add different contributions to this mass production rate. So this is saying if the circumferential stress goes up, more of this material will be produced. If the wall shear stress goes up, less of this material will be produced. And these Ks are the rates of how a difference, so these are gain factors. If you think all the way back to this like feedback loop, this would be one of the gain parameters. This is the stimulus, and this is the biological response. And the gain tells us how is that stimulus translated into a biological response. And you can have different biological quantities that are all regulated. Maybe going back to a question we had earlier, how would I impair one of the sensors? Like what happens if one of the sensors isn't working well?
You have a delay, maybe.
Oh, we could, that's okay. You could have a delay, but what if it's just not picking up the signal, or just picking the signal up less than it should maybe? What could we change? Yeah. Yeah, exactly. Worst case, the gain is 0. So that would mean, let's say, the wall shear stress gain is 0. That means this mass production just does not depend on wall shear stress. No matter what the wall shear stress is doing, this is not picking up on it. Or we could at least like make it very small. So like it picks up on it a little bit, but not as like it should in healthy tissue. Yeah, and so this is what the mass production has. And this in here, all this function here, this is also sometimes called the stimulus function. And the stimulus, what happens in homeostasis when everything is like perfectly balanced? Yeah?
All the deltas are 0.
Yeah.
And the mass production is 0.
It's not 0.
And 0.
Yeah. The deltas are all 0, and the mass production is just, I forgot the name of this, like the natural mass production you have in mature tissue. Yeah, but the stimulus function is 1. And only when we perturb it from its homeostatic set points, the deltas are greater or smaller than 0, and then we have more or less mass production. Yeah?
Are the components interacting with each other in the sense that the production and other output would be perturbing the other alpha 1? Or does that happen via the delta sigmas, the delta t, because they sort of self-regulate each other?
No, so this is a good, I don't think this has anybody modeled it with an interaction. This is basically assuming these are all orthogonal stimuli. Like the wall shear stress has nothing to do with the circumferential stress. They can be mechanically related. Obviously, through fluid dynamics, these might, also not really, because you could change the pressure level independently of the velocity. But there could be some other reason how these are coupled. But in here, they are distinct stimuli. Like you're just looking at any interaction. And technically, you could also say this is just like a linearized response, like for small deviations. But if there's like a massive increase in pressure, maybe like this is not actually a linear response, but more like a sigmoid function. Like it smoothly transitions between, because like the stimulus might be saturated at some point. Like if you increase the pressure 100 times, probably this is not gonna have 100 times as much mass production, because there will also be limitations on like how much mass you can actually produce. So like you could see this as like a linearized response around the homeostatic set point. Yeah?
Also good to think about, so why is there a minus
Ah,
of the wall shear stress?
yeah. Why is there minus? Yeah. What if the wall shear stress gets higher? What does the vessel do?
Should it get bigger or smaller?
The radius or
Yeah.
radius probably will go bigger.
Yeah, you want the radius to increase indeed, because you want to accommodate more flow, right? And how do you make the radius go up? Because that's the funny thing, right? There's only one stiffness function for circumferential stress and for wall shear stress. They're
Yeah.
brought together here.
Yeah.
And indeed, you want the radius to go up, but how do you accomplish that if your only thing you can turn is the production of wall material? Yeah, you want to make it slightly weaker so that the pressure makes it bigger, right? And so that's why the minus is there, because as soon as wall shear stress goes up, the vessel needs to weaken a little bit so that it can get bigger.
Yeah.
Whereas for circumferential stress, you actually want to compensate for it. So there you want to, because that typically occurs when pressure goes up, and when pressure goes up, what you want to have is you want your wall to thicken, so you want to produce more material. So that's why there's a plus before the first term and a minus before the.
And this is actually a big difference to the kinematic growth model. In the kinematic growth model, we said we're controlling the thickness with the lambda. And we had an equation of how the thickness is controlled with the lambda. Here, there are no kinematics here. Like we're just saying we're adding or removing mass. And then the actual like mechanical mechanism we have to find through like the mechanical equilibrium. The only thing we're prescribing is, does the mass go up or down? We're not directly prescribing radius or thickness. So this is why we need that like sort of detour. But this is what the cells do as well. The cells don't know if there's a radius or a thickness. They just add stuff or they remove stuff. For this like preferred mechanical environment, this is also like borrowed from Jay's lectures. He's like, well, what the cells kind of do is like, how do you measure mechanical environments? So like they would like look left and right and like see like, oh, how much am I being stretched or stretched? There's also another point of discussion. Should this be a stress or a stretch or something else or stiffness?
Yes.
Doesn't matter. These are all model assumptions, but it is a little bit more, ever so slightly more motivated by the microstructure. So the cells just see, am I stressed more or less than I usually want? And according to that, more constituents are deposited or not. But this has nothing to do with the geometry or anything else. That's a very good point, so we have that. We have the material behavior. We have the production rate. What we now need is also a removal rate. So we also need to describe how are things removed from the tissue. And typically what people assume it's like a Poisson process or just decays exponentially over time. And often we include like some term that just depends on the stress. So if it's more stressed, and the higher the stress is, like the more gets removed. But technically you can also model this in different ways. And so if you put it all together, what was the question? Oh, okay. If you put it all together, now we can finally compute the constituent-specific strain energy density function. So this is W alpha hat, and this is all weighed by the density of the material. So and this looks pretty much like the integral we saw earlier with what is the remaining density of the material. The only thing that changes is we now also have the strain energy function in here. And the argument of the strain energy function is this combined deformation gradient that tells me what is the deformation of a tissue constituent alpha that got added at time tau, what is its deformation at time s. And then we do the same thing as we did with the mass balance. We have the strain energy of the original material, plus all the strain energies summed up of all the different constituents that got added at all the previous times tau. And we have the production rate and how much of that constituent added at time tau is still remaining at time s. And again, this deformation gradient here we get from taking the deposition stretch, using the total deformation at time tau, and the inverse to get it back to the reference configuration, and then use the total deformation at time s to get it to its current configuration. Well, does that make sense? So it's like basically a density weighted sum of all the different constituent strain energies stretched at all the different times when they were added. Yeah. And it still depends on s. So in the end, technically we should rename this inside the integral because here's an s and here's an s. Yeah. But in the end, it still depends on s. We're only integrating over tau. So we're integrating over all the previous times from 0 to the current one, but this still depends on the current deformation. Yeah. Questions? This is the final integral of the constraint mixture theory. This is all we need. Yeah. I think next might be a short, oh, no. Oh yeah, there's some special cases. Special case 1 is that we are right before a perturbation. So you could say, and typically we set time 0 as the time right before a perturbation. So we say at time 0, everything is in homeostasis, and then we perturb it in some way, like we increase the blood pressure, for example. And so right before a perturbation would be at time 0. Obviously at time 0, this deformation gradient here, yeah, that's the same deformation. Wait, not sure if this is correct, because there should still be a tensor in here, not just a 0. I mean, it's kind of correct. So it's W alpha at time 0, but it should be W alpha evaluated at the deposition stretch. The other like special case is if the configuration doesn't change. So if we are before a perturbation and then we don't perturb it, we don't perturb our tissue at all, then we still have. It doesn't mean that the tissue is static, we just don't perturb it. So that just means there is still deposition and there's still degradation. It's just balancing. In which case, the strain energy just depends on the current time and not on the previous times. I think the more exciting special case is this one, where tissue is in perfect maintenance. So that means, again, it's undisturbed. So that means our stimulus, what happens to the stimulus function if the tissue is undisturbed and in homeostasis?
Constant to the part that you had, like the 1 minus is cancelling.
Mm-hmm. Yeah, it's like all the deltas are 0, and then the whole production rate is just this M0 that was in front of the parentheses. Then we can assume this is the uppercase Q is the remaining tissue at time 0, and then the lowercase q just models with this like decay equation how much tissue added at time tau is still remaining at time s. And if we plugged it in here, so this is the decay of the original material, and this is the production and degradation. And if the tissue is in perfect balance and doesn't change, that means that this evolving density just remains the density at time point 0. So if you plug in for rho alpha of s, just rho alpha of 0, we can rearrange this equation, and then you should see that we have twice the same term, 1 minus this exponential function, which then cancels out, and we can see that in perfect maintenance, there's this like balance between adding new mass and removing mass, which is pretty nice. So basically, if I add stuff at the same rate as I remove it, we still have this deposition and degradation of new material, but the density never changes. Like from the outside, it looks like, oh, this is like static material, but there's still like this exchange of the cells happening. It's just they get added and removed at the same rate, basically.
Or also you can, I mean, one of the cases that I can think about is like it does it periodically, kind of in a sinusoidal way. Like,
oh, interesting.
and then the average would look,
yeah,
I would guess it would look something similar.
Yeah.
But the actual dynamics are slightly different.
That's true. I think in this simple model, as soon as you perturb, like I don't think you would have this like oscillation around a set point that I showed in the beginning.
Yeah,
I think with this model, it wouldn't be possible. It would always just decay back to a constant value. Which is this is actually a good point, because something I should also say is that these homeostatic, this whole concept is mechanical homeostasis. It's not mechanical homostasis. So it's just homeostasis means it returns to something similar, but not exactly to the same thing. So that's why initially it was shown, like there was like this dotted line and there was like some oscillation around the set point. Technically it just has to come to something, like it has to return to something similar, not necessarily exactly the same thing. However, in all of these models, like the homeostasis is like defined. There is no range or anything in these models, but that's more like it's easier to model that way. But technically, they just need to return within a range. Same as like your body temperature is never perfectly exactly the same and doesn't have to be. There's like a whole range for you that's still fine, and obviously there's a range where it's not fine anymore. Other questions or remarks? So I think we should have an example soon. This is another one. So this is not an example, but maybe you can already, I think we already alluded at, this might be a little bit expensive to do, but how expensive actually is it? So at each of those n, let's say this integral, we don't need, in rare special cases, you can actually analytically integrate. So typically we use numerical integration. So the easiest case, you just use like some trapezoidal rule and you just cut up your integral into like a discrete number of n sub-intervals. How does the computational cost scale with n? And keep in, so as a hint, at every new time step, we have to sum up all the previous time steps. So what's the computational complexity? How does the cost of this method, we don't know what the actual cost is, like we don't know what we actually have to do at every time step, we just want to know how does our cost increase with the number of time steps? Yeah, why? Yeah, that's it. It's like if you, I think, it's like the Gauss summation formula. It has complexity n squared. It's always, I kind of wanted to not have that, but yeah, if you think about the kinematic growth model, how does that scale? That's just linear. You just need to evaluate every new time step independently of the previous ones, right? So that's why this is just complexity n, whereas the constraint mixture model is complexity n squared, which of course makes it even like the longer you want to go into the future, the worse it gets. Again, there are like some strategies now where you can like smartly evaluate those integrals and like decide what you need to keep and what not, but it requires extra effort, and like plain evaluating these integrals scales with n squared. Yeah. Okay, let's do an example. Okay, this was enough integrals and equations. And so now if you run example 2, so that's the same thing as before. There's like our same idealized perfectly cylindrical blood vessel. You can apply a certain increase in blood pressure. Obviously, there's like way more constants in there now that already have been set to something more or less meaningful. But yeah, I would say just, try different increases in pressure and just see what happens. And now there's also like a couple of things you could like play around with. So here the input file already includes like a sweep over different like pressure increases, but you could also see like, hey, what happens if I like change the turnover days? Like what if it takes longer to turn over or is quicker to turn over? And like what if like constituents are like more sensitive to these stimuli? Another one limitations in the beginning, I talked about pressure and wall shear stress as like the two key regulators. This only includes the pressure stimulus. I want to keep it easy. This does not sense wall shear stress. It has no idea what that is. Does it work? Okay. Okay, what do you see? I think I also made a video. Okay, so I don't think this is like what the script is outputting, but like I made this like combined. I tried to basically plot everything what's going on in the model. So again, like the pressure increases, and then you can see initially all the constituent stresses shoot up, And yeah, what is that constant blue line here? Can I explain why there's like constant here? Yeah?
Is it elastin?
Why is it constant?
Must we assume it doesn't decay?
Yeah, that's it. Yeah. So now there's only a change, at the very least, there's only a change in mass in smooth muscle cell and collagen. So they change. And you can also see that now both radius and thickness simultaneously adjust. Because now we didn't like prescribe, as with the kinematic growth model, we specifically said we are modeling a change in radius. Here, all we do is we model a change in mass, and then that combined with the balance of linear momentum tells us what is the trade-off between like thickness and radius. But obviously we know that if we increase the blood pressure, the thickness should go up, and obviously like this change is much more, like this is like 45 or maybe 50% change in thickness, and there's a much minor change in radius, but we're not constraining that. That's like a model output is like what is the trade-off between radius and thickness. And we can see, obviously, yeah, where's this mass coming from? Like obviously if it gets thicker with the same radius, there must have been mass produced, and now here we can see elastin stayed the same, but we produced smooth muscle cell and collagen. Obviously, if that makes biological sense that they're both produced at the same time, up for debate, but I think the file has almost the same parameters for the two of them, and they're just mixed together. So we're not taking into account like different layers or anything, but yeah. What you now also can try if you go to the input file, you can actually simulate your very first aneurysm. So if you go to the input file and where it says insult, so currently there's this like pressure insult, just set it to 0. And then there is a factor for elastin surviving. That's basically just a fraction of how much elastin are we taking away. Because one, yeah, do you want to say something about aneurysms?
No, go ahead. Yeah.
Or like basically, yeah, how they are created is like, yeah, you lose elastin integrity. So you could also model it as like a loss of elastin stiffness. But there's like in some way elastin uses its ability to like bear the mechanical load. And since elastin does not turn over, like you're not getting any new elastin. So like that insult now has to be taken up by the other constituents that somehow have to make up for that.
And that
Yeah.
does not always cause aneurysm, eh? So
Yeah.
I mean, with
Yeah.
aging, for example, we
Yeah.
also lose
That's
elastin
right.
eventually.
Yeah.
It just takes a lot of time.
Yeah.
But most of these people don't have an aneurysm.
Yeah.
It's just a matter of how do the other constituents catch up?
Yeah.
Can they catch
Yeah.
up with the loss?
Yeah.
So yeah, we're still not fully sure also biologically like why.
Yeah.
Why do some people get an aneurysm indeed? I mean,
Yeah.
it's likely elastin related, but still.
Yeah.
Yeah.
Yeah, right. This is not the definitive model of like
No,
of how an aneurysm is. But yeah.
That is a bit.
That is,
That's
yeah,
right.
yeah.
Yeah.
Yeah. That's true. And then you also change the stiffness. So that's also something you could evaluate. Once you have this new mixture, you can also evaluate what is now the elastic behavior of that new mixture. So if you remove elastin and you have more of the other constituents, it will also be elastically less compliant and like more stiff. Yeah.
And that will change blood pressure again.
Oh yeah, right, yeah. And there's many other feedback loops, right, yeah. There's more feedback loops in here. Okay, so if you see, so I made another video for one of the aneurysm cases. So here, that parameter I think is set to 30%, so that just means that the elastin, I guess you would have to call it the elastin fraction, which initially starts at 1. Just relatively, we are removing 70% of the elastin. So now at the end it goes to what used to be 1 goes to 0.3. And again, you can see the initial elastic response. Just the fact that we remove the elastin already makes the radius increase and the thickness decrease. It's just we're removing something. Think of it like we're cutting a part away of that stressed tissue, so instantly it moves a little bit. The mass fraction goes down, that's what we prescribed. And then you can see this is made up now by, again, producing more smooth muscle and collagen. And so now thickness stays more or less the same, but the radius increases. But this, I cut it off here for plotting, but you can kind of tell this looks like it's going to stabilize. So it's going to find a new equilibrium where the smooth muscle cells and collagen are again in homeostasis. The stress of the elastin changed. But new homeostasis does not mean it returns to the same state. Like it just finds a new equilibrium where these constituents are in homeostasis, but it found a new vessel configuration, basically. And what is exciting is if you give that a severe injury, a much more severe injury, so now the elastin goes all the way down, I forgot what it was, like maybe, 3%, okay. Again, we have that like initial elastic response, and now we see what happens. So now elastin and smooth muscle cells, they're trying to catch up and like producing more, but they're not able to produce enough or produce new material quickly enough to catch up with that. So the mass just keeps growing, and also the radius keeps growing. Again, this does not mean we've now, with this like simple equation, we found a tool to predict aneurysm growth, but this is to illustrate that this property of is this a stable process or not is not something we impose, but it's an output of the model. And it depends, what does it depend on? Like in this case, how much basically there will be a threshold of how much elastin I can lose in this model, and it still recovers a new equilibrium. And obviously you can try these things for yourself by like changing how much elastin you degrade. So you can like change the insult and then also have like a parameter sweep and like see how much would I have, like where's the threshold, what could it still take. And there's people wrote like more theoretical papers about can we use that kind of stability theory as like a sort of like biomarker. Are there ways of quantifying how stable or unstable an adaptation process will be? Okay. I will briefly, we're almost at the end, I think. I think we said until 4, right? Where am I? Yeah. 4:30. Oh, 4:30. Oh, easy. Okay. Should we maybe take, you know what, let's take a little 5-minute break. Okay, so like in the last 20-ish minutes, I'll show you 2 submodels of the constraint mixture model. They're also like, pretty cool ideas. And so they're both motivated by the fact that nobody wants to solve these integrals. And they are a little bit annoying to implement, and they're also annoying to compute. And the first subgroup of models, or model is like the homogenized constraint mixture model. It was introduced by Christian Cyron in 2016, who was a postdoc with Jay. And his idea was the following. Because like we already said, like, well, it's super annoying if I need to keep track of all these constituents, even though they're like decaying over time. Like, why do I need to keep track of something that was like added 10 years ago? This is like also not how the body works, or the cells work. Like the cells do not keep a memory over like the last 10 years. And so the idea of the homogenized constraint mixture model is sort of to have this like Maxwell fluid model with a motor. And what it does is it has a spring element, which is the elastic stiffness of the tissue, and it has a dashpot or damper that includes turnover, so it includes production and removal. It only it represents degradation, not production. The production comes in here. The production is represented by this motor unit. So this motor unit always restores the so in this case it's a pre-stress, but we said if we know the constituent strain energy function, we can switch between a pre-stress or pre-stretch. And so what this is doing here, this is like basically pulling along those 2 ends always trying to restore that like pre-stress. And then here, and this is parallel to the spring and dashpot. So what happens if I just leave it alone? If I don't do anything to the system, it will always like make sure that here we always have the pre-stress. And over time also this like dashpot will relax. And so in the end there's just an equilibrium between the pre-stress here, and then the pre-stress will also be in that spring. And when every time I deflect that system, so let's say it is currently in homeostasis and like I pull on it, then since there's this motor unit that is pulling with that pre-stress, that motor unit over time will again pull in that dashpot and make sure at an infinite amount of time, this dashpot again is like fully in equilibrium, and the stress in the spring matches the stress or the pre-stress in this motor unit. And so the idea is that those two together can represent the same mechanism as this like full constraint mixture model where I track all these constituents. It's basically like modeling like the same effect without having to track the configurations. We're still modeling individual constituents. So this whole Maxwell fluid model is for one constituent. They individually make sure that they set their own pre-stress again. And we still have to like sum over the whole mixture, but we do not need to sum over those previous configurations because that whole process is already sort of like included in this rate model. So it's more like a rate model instead of like an integral over all previous time steps. Does that roughly make sense? Or any questions how that works? We need to define two things. The growth is now also represented by this mass production function. Has anybody seen something like that before? Sorry? Yeah, exactly. So this we had a very similar expression when we looked at the kinematic growth theory. We also have a production term. The only difference is now this is a mass production term. We're just saying there is more of a constituent, whereas in the kinematic growth model, we just said there is more of the whole tissue in a certain direction. Here, we also have a rate equation, but at this time, it's really modeling the increase or decrease in mass of a tissue constituent. So it's similar, but it's somewhere in between the constraint mixture model and the kinematic growth model. And then for remodeling, we have basically the same equation. The remodeling is now defined by the stretch, but we also have a time evolution equation of that's controlled by how much the current stretch varies with respect to the homeostatic stretch. Same with the goal of whenever it deviates, it will try to return to that. But also tissue constituent specific. Yeah. And so, yeah, you can see it as an in-between between the kinematic growth theory. So at the end in 3D, you can write this as a product of three tensors, an elastic tensor, a growth tensor, and a remodeling tensor. And they're both represented by these two ODEs. So now you only have to solve ODEs. You do not need to do this heredity integral anymore. You like sum over all previous configurations. Yeah, there's the comparison. Yeah, how do we think? How does the computational cost scale now compared to the full model? Yeah. Linear. Yeah, now it just scales linear because we basically just look at the previous time step and the current time step. The other thing is, since we have this Maxwell fluid model, we just have what is, maybe I should have said that first. Or can anybody guess why is it called homogenized? How do we homogenize? Where does the homogenization take place? There's like one specific variable over which we're homogenizing. Yeah?
in time.
Yeah, exactly. We homogenize in time. We don't care about all those different configurations of the tissue. We just said there's a mean configuration of all the tissues that's represented by this like spring, dashpot, and motor unit. Yeah, so when do we think this is a good approximation of the full model, or when is it not? When can I do this homogenization and when not? Basically, since we're homogenizing over time, try to think what could change over time and what shouldn't change over time. Any ideas? Maybe let's start, if we go back to the schematic. What is one thing that's constant here that doesn't necessarily have to be constant? The elasticity. You mean here, this stiffness here? It could change, but technically we also didn't change that in the full model. One thing, and we also didn't change it in the example. One thing that we did change was like G alpha was written as G alpha of tau. So technically the deposition stretch could change. Like it doesn't, we never specified that they're always deposited the same. But here we have constant pre-stress. So if that were to change, we are approximating that. Also change, like this is also a constant here. Like the turnover rates, the degradation rate is also constant. Technically that could change. But I think more importantly is another thing that could change is like if the configuration under which the constituents were deposited, if that changes a lot, then this homogenization is also not good. So if I have like a tissue, I don't know, you have it in this configuration, I add constituents, then I stretch a lot, add them again, then I add them in this configuration again. If that changes a lot, when like the configuration at which tissue was deposited, then the homogenization is not a good approximation. But if it's always deposited with the same deposition stretch at like similar configurations, then this is a very reasonable approximation. Yeah?
Would that also hold if you have a different deposition stress in time, but that is periodic?
Yeah.
Would that also
If it's periodic, are you saying like it averages out? Oh, yeah, maybe that could work, yeah. Yeah, if it just averages out over time, yeah. Yeah. Okay, is that what I had here? Yeah. Oh yeah, fast insults, that's another one. So if you have a very fast insult, obviously like you're adding constituents with very different configurations. Like if the pressure suddenly shoots up, then your configuration changes quickly, and then also the deposition configurations change quickly. There is another example. Let's do the third, like the final theory first, and then at the end we compare them all. Let's do it this way. Because there is another, theory, and that's called the equilibrated constraint mixture theory. So that's yet another subcategory, and maybe as you can already tell, the idea is that we are finding the state where the tissue is already in equilibrium again. So if you think about the examples that we ran earlier, we apply an insult, the tissue adapts in some way, and then it finds like a new stable equilibrium. What if we could directly predict that without having to go through the time course? And there's actually a way to do that, because what do we know about this new equilibrium? Like think of like the hypertensive case, like thickness goes up and then it stabilizes. What do we know about this like final endpoint? There's one thing that we know about this configuration.
Stimulus is back to 1.
Exactly, yeah. Yeah, it's again in homeostasis, like it's stabilized, so it must be in homeostasis. So we can set the stimulus function. So I don't think I introduced it earlier, but epsilon is the stimulus function. You just set it to 1 because we know all the deltas will be 0 again. We know it's a mechanical equilibrium, and we know that the remodeling has been completed. So that just means we are in the state of like continuous maintenance. Like there's still turnover, there's still stuff being added and removed, but it doesn't change anymore. And we can use all these facts and directly find the equilibrium at the end. Yeah, so that's super useful. There's one caveat. What's the caveat with that? What can you not do with the equilibrated theory? Yeah?
When there's no equilibrium.
Exactly. Exactly. If there is no equilibrium, whatever equation we come up, so here in the end it's not time integration, it's just a root finding problem. But if there's no equilibrium, we should not find a problem. We would not be able to find a solution to this. So it only helps when there is an equilibrium. Yeah.
And so the deltas, do they necessarily need to be all 0, or it can also be that combination of such that stimulus is back to 1?
They don't have, that's a good point, they don't have to be 0. I said it wrong, yeah, you're right. The deltas don't have to be 0, they just have to sum up to 1. Because if they were all 0, that just means it didn't change at all. But if you have more than one stimulus, let's say you have wall shear stress and intramural stress, there might be a different balance between the two. But they still sum up to 0. Yeah, that's very, very important distinction, yeah. Yeah, and so I'd say as like the final, okay, this is like the scalar equation for our example here. I would say if you run, there's like 2 examples. So you can try to run example 3. So up here, it contains 3 different theories. So you can compare the constraint mixture model, the homogenized, and in this case also kinematic growth. Do I have that? Okay, so here I made a video that compares all 3. Sorry, all 4. So all 3 constraint mixture and the kinematic growth model. So this is like the hypertension case where we just increase the pressure. So we can see a couple of things. Obviously, the kinematic growth model is like a very different model. It has different parameters. So this is like made so it yields similar results, but it works in a very different way. So it doesn't really make sense to compare that to the constraint mixture model. But you can see, since we only modeled an increase in thickness, the radius goes back to 1 in the kinematic growth model, like this purple curve. Then you can see the homogenized model tracks the full model pretty well. And all the equilibrated model does is it provides this line here. It just says, this will be the long-term equilibrium. We don't know how we got there, but we know this is like where the blood vessel finds like its new equilibrium with the increased pressure. And of course, what you can also do is, in this simple case, you can use the equilibrated model as like a stability criterion. Can I find a solution or can I not find a solution? And if you can find a solution in this case, like very simplified case, then it means there will be no equilibrium that the transient theories will converge to. Yeah. Yes?
I have a question. Is it in any way meaningful to say that the equilibrated CMM can be considered the asymptotic values to which all the transient ones will converge?
Yeah. And there's also a recent paper out of Jay's group from like this year where they compared the different theories in 3D, and then you can see like how well they agree, or in which cases like a solution doesn't exist anymore. Yeah. More questions for this? I would say, since we're running a little bit out of time, I would say we have the examples open and you can play around with them. I show you, let's do the following. I show you a few more slides with like current research directions, stability. And then I would say we go back to the coding examples, and like as long or little as you want, you can play around with them. I can walk around a little bit, and then you can leave whenever you want. But it's a presentation-wise, I think this is the last thing I wanted to show. So future perspective. So what are people currently doing? This is obviously from my computational perspective. There's actually one good example I also wanted to show. How is any of this relevant clinically? And so, does anybody know what the Fontan procedure is? Yeah? Do you briefly want to explain?
I think, if I'm not wrong, it's done in children that are born with a certain defect on the ventricle, so they don't have
The heart, yeah.
on the
Technically, they have like half a functional heart. Yeah.
Yeah. So you cannot then, you don't have the connection to the aorta or the correct way of pumping heart in the aorta, so you connect it by adding a graft between the only ventricle they have, or not this healthy ventricle they have, directly to the aorta.
Something like, yeah. So like they have half a functioning heart, and then you're trying to. It's a big problem if that functioning half is the right half, which pumps normally into the lungs, but it's even more important to pump blood into the body. So you turn the right side into a left side, and then you have to rewire or like replumb basically how blood flows back to the heart. It's like a series of surgeries. But a big challenge is, like, in the end, you need to reconnect blood vessels. You need to take blood vessels where they weren't and reconnect them to something else. What is a huge challenge when you do that in children? They grow. So if you put in a graft in a child that's maybe a few years old, and ideally you want him to survive several decades, the graft will need to grow. So if you put in a graft out of synthetic material, that's not really going to work. And a new idea that people came up with is to have like a tissue engineered graft. So there's like a scaffold that you put in, and ideally then the scaffold like is seeded by the patient's own cells, and the scaffold degrades over time. So you're basically creating a new vessel in that child with the child's own cells. So there's no like rejection or anything. You're just basically creating a new vessel. And people did that in humans, and one thing they found, which is very scary when you put in a graft, is, so this is after 1 week. Okay, and we see what happened after 6 weeks. Like it's the nose, so it narrowed. So that's something you want to avoid at all costs. It, like suddenly the graft you put in, like it started constricting, then people got very scared and then went back to animal experiments and tried to recreate that, and people also did computational modeling in that. And then what they found was it does the nose initially, but then it opens up again. And that was something that could be recreated with the constrained mixture models. So they're a little bit more complicated because you also have this like part that degrades over time. And then you could see there's like, I think the problem was like there's a lot of inflammation in the beginning. That's sort of like the case over time. And that led to it narrowing, but then like the inflammation goes down, the mechanics take over, and then it opens up again. So this was more like and then, they could continue with their like, I think they're doing a clinical trial with these. Okay, so this is like one of the more recent clinical applications. Another interesting avenue, this is an example by Linda Irons. We just talked about like these parameters. There's like gain factors, there's stimulus functions, but none of that has actually anything to do with biology. These are basically just like surrogate models. So people also coupled these growth and remodeling models with systems biology models. And then you have like all these networks. So, so you also input the mechanical state as stress and wall shear stress. But at the end, the biological response that you get is not something we prescribe with like a few simple equations, but actually something that's predicted by this network. And then you can also change these interactions in that network and see like what would happen if I give a certain medication, for example, or if certain gene mutations are present. And something else that I've been working on is we only talked about very simplified information from the blood. So we only talked about blood pressure and wall shear stress, which are both scalars. But in the end, the job of the blood vessel is to pump blood. And so what we looked into was, what is the local interaction between the blood flow and the vessel wall remodeling? So, because if you imagine, like you have, even like in the simple case of hypertension, you saw there's like a lot of like thickening and like changes in radius, which obviously then also changes the fluid dynamics on the inside. And so we developed a model how to couple the 3D growth and remodeling like to the 3D fluid dynamics in the blood vessel. And like one challenge of that is that you're dealing with like very different time scales. So if you look at the x-axis of all the plots we looked at today, those were at least like on the order of like a few weeks, if not years. But obviously the fluid dynamics happen like more in our simulations on a time scale of milliseconds. So you somehow need to couple those two fields. And so this is one example. So here in the top row, this is again a very simplified blood vessel. This is supposed to be a mouse aorta. It's just a cylinder. But the parameters were taken from measurements in mice. It's a little bit cut off. But at the top, we just assumed that the wall shear stress scales with the inverse of the radius to the third power. And at the bottom, we actually coupled it to the fluid dynamics. And the insult is almost the same as in your model. So here, we assume in the middle, we are losing elastin. So in this case, we reduce the stiffness of the elastin. And we also assumed that we lose mechanosensation, so that the tissue cannot sense the wall shear stress anymore in this region. But only in the top region. So down here, it's technically still healthy tissue. And you can see, so this is with fluid-solid growth interaction, where this growth in the solid is actually coupled to the velocity and the pressure from a fluid dynamics simulation. And one thing that we saw was, even in the healthy region, like basically the biggest difference you see in the healthy region, because here you sort of assume that the aneurysm and the healthy regions are like decoupled, because the fluid stress only depends on the third power of the radius. But since we're here, we actually coupled it with the fluid dynamics, and this aneurysm basically makes the fluid transition upwards. It's sort of like pulling that lower wall inside as well. If that plays a big role is another question. So this was more like a computational paper where we like try to figure out how to couple these. I would say aneurysm development is, I don't know if that's the application where you need this method. Another big limitation is this is all steady state flow. So this is like just constant flow, whereas everything in the body, at least like in the greater blood vessels, is pulsatile. So as an extension of that, one thing we wanted to look at is how does pulsatility affect this growth? Because currently in all these growth models, everything is like constant and steady state. But technically, these cells are never measuring constant flow. So currently, one of my PhD students is working on extending that into pulsatile flow. And then we would be extracting those stimulus functions like the intramural stress and the wall shear stress. We're thinking about what parts of those over the cardiac cycle actually matter for the growth and remodeling. Is it the maximum value? Is it the minimum value? Is it the mean value? Or is it like the amplitude of these values? Because once we have that pulsatile flow simulation, we can choose which of these we want to couple with the growth and remodeling simulation. Are there questions? So for the last part, it's just a very brief overview, but I thought it would be nice to end like a little bit of research to see that we're using these things. Obviously from a very computational perspective. So I did not tell you anything about like the experimental side or the clinical side. This is really just how do we solve these equations. Okay. I would say let's end it at this point.